Okay, it's 5:30, so let's go ahead and get started today. All right, good afternoon, everybody. How's everyone doing today?
Pretty good, pretty good.
Good? Yeah, good to hear it. So for those of you guys in senior design, I heard they dropped kind of a bombshell on you guys last week. So I know they're having the ECS virtual showcase this Friday. So I'm sorry about that. That's tough. I mean, to prepare something, I think, on that sort of notice is it's pretty tough. So, definitely feel bad for you guys. So, if there's anything I can do, I know I'm not really involved much with senior design, but, if there's anything I can do, at least for this class to make things easier, for you guys, then definitely let me know, because, that's a tough pill to swallow, I think, on such short notice. Okay.
I'll just give us an A.
That I can't do, but I can at least make things better for your time, at least to give you guys more flexibility on that. Okay, so this is our first lecture back because last Wednesday we got cut off because of Spectrum. So once again, I apologize for that. So I'm hoping that the internet stays stable for the rest of the semester. So for those of you, I guess everyone that wasn't able to watch the rest of the lecture, I posted the asynchronous lecture the following morning on, and that one's important for your final project, because that's that's where we learned how to do higher order schemes for finite difference. I think the majority of you guys are at least doing finite difference for your final project, so that's definitely one to take a look. So I got some questions over the weekend on the project. I think one mostly from Rick. Maybe Rick's not here right now. He was asking about the signs and some of the convection terms. So at first, I took a brief look at it last night when he asked me, and I thought the signs were correct. But now that I'm looking at it again and comparing it to the example that I made last week, I think there might be a couple typos or two. Based on the signs of the coefficients. So I'm going to take a look at that tonight and then have an update for you guys, just so it's not as confusing for you guys when you're looking at the starter code. Interestingly, though, even with it might be one of those things where I had kind of two wrongs that kind of cancel out each other, because when I run my solution, it seems to work pretty well. But I think there's some sign mismatches that's confusing with the example code that I posted last week. So. Let me take a look at that, and then I'll get back to you guys on that. Okay, so the plan for today is we're going to continue on with higher order schemes. So on last Wednesday, the thing that we did asynchronously was a higher order scheme for finite difference. So today we're going to learn how to do higher order schemes for finite volumes. So kind of coming back to finite volumes for a bit. So it's a bit more complicated. So I'm kind of blocked off the whole day for that. And then once we're done with that, then we're probably going to spend 2 lectures doing unsteady problems for finite volumes. So I expect that'll be about 2 lectures. And then after that, we have 1 more lecture left. So what I've been doing was I've been talking with Dr. Sanders, who teaches another class that's actually taking place at the same time. And we kind of agreed to do like a seminar swap. So what's going to happen is that next Wednesday, what I'm going to do, we're not going to learn anything new. But what I'm going to tell you, what I'm going to prepare is, I'm going to just kind of tell you guys a little bit of the research that I've done in the past, involving a lot of this stuff. Because I think, we spent a lot of time in this class, like really going really deep and kind of hard at the theory that, we haven't really talked much about the applications. So I really wanted to at least give you guys a glimpse of that before we leave for this semester. So I'm going to do that next Wednesday. So, there's nothing that's going to be, I'm going to test you guys on, or, there's nothing it's not going to be that relevant for your final projects. But I thought, just from the perspective of, just so you guys can kind of see the end point of kind of what we're learning, that's what I'm going to do. So that's going to be next Wednesday. Okay? Oh, Rick, so you just joined. So I read your email last night, and then I didn't really look at the code, but I was looking at it just now, and I think you might be right that there might be a sign mismatch. Or a sign discrepancy between what was in the starter code and the example code that I posted last week. So I'm going to take a look at that tonight, and then kind of give you guys an update for that next week.
Yeah, I was gonna ask about that.
Yeah. So I think you're right. So I think there is a sign missing. So I think I made a couple typos in the starter code, but the interesting thing was I think kind of two typos, two wrongs kind of ended up making a right, and then it ended up making the starter code work. But just for kind of clarity's sake, you know, I need to go and correct that. So let me go and do that, and then I'll kind of get back to you once I sort everything out.
And also, when I was doing the higher order, I saw that you multiplied by a dt, then divided by a dx. But I was trying to refine that in the notes and in the codes. But
yeah, so the final project, it's an unsteady problem. So we there has to be a dt in there because we apply implicit Euler. What you need to do is you kind of need to combine what we did last Wednesday, which we learned, how to replace. Because normally when we do the central difference scheme for the convection term, we do just this, right? Oops. Right. But for the higher order schemes, we have the different scheme that we're going to use. And so what you're going to do for the project is that you're going to take that same convection scheme, the higher order one, and then combine it together with the unsteady term. So remember, the unsteady term, that's where the dt comes from. I think it'll help a lot to kind of write out what that equation looks like on paper first, and then implement those coefficients in code. So there's a little bit of work on paper that you guys need to do just to get those coefficients. And I have kind of the example for the left side, just for you guys for reference. After I corrected it, I need to correct those coefficients. Yeah.
Okay, I'll go ahead and look off for that and get it going and see if I have any issues.
Okay. Yeah, sounds good.
Also, I kept getting this line issue. I believe it was on line 66 when we're getting the square root of x minus xc squared minus yc squared.
Was that the same issue as Alfredo?
I'm not sure.
Maybe we'll talk offline about that, and then we'll see. Yeah.
No worries. Thank you.
Yep. So there's a question on the due date for the final project in the chat. So it's not due May 11th, because May 11th I think is that's during finals week. So it's going to be due the Monday after that. So it's going to be due May 18th. Because I think the original due date was May 11th, because that was the day when we were supposed to originally have our final exam. But we're not having a final exam in this class. But because of the situation, I wanted to give you guys some more time on the final project. So it's going to be due May 18th. So that's the week after that. So I still need time to grade it. So I can't have it due any later than that. But I wanted to give you guys some flexibility, especially with the virtual ECS showcase happening this Friday. And probably a bunch of other crazy stuff that's going to be happening over the next few weeks. That I want to make sure you guys have enough time to really work on the project. And all throughout finals week, so I'm only giving one final exam. So I expect I'll be pretty free and available during finals week. That if you want to, set up a Zoom call to chat, I'll still have my regular office hours so that you guys can come in and chat, and just so you guys can get help on the project. So it'll be due May 18th. So I think one thing I still need to do is I still need to make a rubric for the final report. So I'll probably work on that sometime this week, and I'll have that up. And then once that's up, then I'll have the due date there. But the due date's gonna be May 18th, not May 11th. Okay, any final questions on the project or anything before we get started today? And we're in week 15, yes. So we have this week of lecture, and then next week, and then after that will be finals week. Okay. So there's no more questions. Let's go ahead and get started. So this is a continuation of the recorded lecture that I did last week, where before we did higher order schemes with finite difference. Now we're going to do higher order schemes with finite volumes. Okay. So to kind of start, let me write out one of the surface integrals that we did, or the face integrals, right? Because remember, when we're doing finite volume methods for problems with convection diffusion, at least in 2D, kind of the goal is to evaluate those four integrals, right? The east integral, the north, the south, and the west. Okay? So let me write out one of those again. So let's say that we have the east integral. Okay? So we have integral of phi v dot n minus k gradient of phi dot n ds. Okay. And then when we apply the trapezoidal rule to this guy, then we get the following: little phi sub e u minus k d phi dx on the east face. Okay. In particular, I want to focus on this guy. Okay. And so if I can draw just two cells, okay. So remember, this is the east integral. So I've only just drawn two of the cells here. So I've drawn phi sub c. Remember, that's the central cell, or the cell that we're evaluating this integral for, and its east neighbor. So phi sub big E. Okay. And remember, phi sub little e. What that is the value of our solution at this face, or at the interface in between the two. Okay. And so what we've been doing previously is that, we've been using just a basic central scheme where we said that phi sub e is going to be just the average of the two. Okay. And then the other one, the other kind of basic scheme that we went over was a basic upwind, where if we know the direction of the velocity, we can say that this interface value is going to take the face on the upstream side. So if we know that the value of u is greater than 0, so u is going from left to right like this, okay? Then we know that the upstream value for phi sub little e is going to be phi sub c. Okay? So if we're using a basic upwinding scheme, then phi sub little e is going to equal phi sub c. Okay? So those are kind of the two that we did. We mostly work with this one, at least in developing the equations, but we at least mentioned this one. Okay? Because when we did convection for finite differences, we used the forward or the backward difference scheme to basically fix our stability problem. So this is kind of the finite volume way of fixing that. So the higher order scheme that I'm going to introduce to you guys today is it has a special name, so it's called the Clique scheme. So it's going to basically combine the good parts of the Upwind scheme. So it's going to be a scheme that's totally stable, and it's going to be more accurate than the central scheme. So it kind of combines the best of both worlds and still be even better. Okay? But the price for that is that it's a bit complicated. Okay. Are there any questions on this? Okay. Okay. Right. So just like we saw with higher order finite differences, kind of the way that you get higher order schemes is that you involve more neighbors. So right now for this phi sub little e, we only have two neighbors that we're considering. But if we kind of expand our radius and we include more neighbors, then that's going to increase our accuracy. So if you look into the literature, there's even for finite difference, there's tons and tons of different ways that you can achieve higher accuracy by involving more neighbors. So the literature goes very, very deep on this. So we're going to go over just one scheme that's really popular. It's called the Clique scheme, and it's actually an acronym. Right? So I'm going to kind of draw this out here. So the acronym stands for, let me see, quadratic, upwind, interpolation. And then there's a 4 for convective kinematics. So the name isn't important, but you know, if you see the Clique scheme with all capital letters, just know that it's an acronym that it stands for this. Okay? So the kind of the key parts that I want you guys to focus on are kind of the first 2 letters, quadratic and upwind. Okay. So the reason it's quadratic is that we're going to, instead of using a linear function that approximates the face value in between phi sub e and phi sub e, we're going to use a quadratic function. So that's going to involve one additional cell that we need to do. Okay. And then the other part, upwind, you know, that tells us that this scheme is going to be unconditionally stable. So when you're using the Clique scheme, you don't have to worry so much about refining your mesh, or you don't have to worry about the Peckley number, which, remember, that was our metric before to kind of gauge whether a convective scheme was going to be stable or not. But since the Clique scheme is going to be upwind, you don't have to worry about that at all. You can kind of use whatever mesh that you want. Granted, you know, you still have to worry about accuracy, but you know, stability won't be a concern. And so today we're going to learn how to implement, or how to get the coefficients for a quick higher order scheme. Okay. Any questions on this? Okay. Okay, so let's see how it works in practice. Okay. So remember, before, when we approximated phi sub little e, we only used 2 neighbors. Okay, so we only use, you know, just the 2 that were bordering the face. And with 2, if you think of it in terms of just math, right? So if you have 2 points, you can make a line, right? But so if you include 1 additional point, you can actually create a quadratic function. Okay? So each of the formulas that all the formulas that we're going to have is we're going to compute phi sub e with 3 cell values. And so let me show you how this works. So because it's 3, there's actually kind of 2 different flavors that we can use for this. So let me draw kind of the let me work it out in 1 dimension, and then we'll see how it works in 2. Okay. So here I've drawn a line. Okay. And I've drawn our cell of interest. So that, remember, that's phi sub c. And then let's say that we want to approximate this guy. Okay. So we want to approximate the value of the solution at that nodal point. So that's the interface between phi sub c and some of the other cells. Okay. So let me draw some of the other cell values here. So of course we have the neighbor on the east, on the right side. So that's going to be phi sub e. Okay. We also have our neighbor on the left side, so this is going to be phi sub w. And then a newcomer here is going to be our neighbor that's 2 away on the east. So I'm going to call that phi sub 2e. Okay. Okay. So one way that we can approximate phi sub little e is if we include kind of these three guys right here. Okay. So if we include the west neighbor into our approximation, it's going to look like this. So phi sub little e is going to be minus 1/8 phi sub w plus 3/4 phi sub c plus 3/8 phi sub e. Okay. So that's one form of the one way to form the Clique scheme. Okay. So we kind of have a like a moving picture frame that includes kind of these three terms right here. Okay. But then what if we kind of shift that over to the right a little bit? So then what if we actually include these three? Okay. So then we get a kind of another flavor of the Clique scheme. So if you can imagine, you know, this this thing that I just drew here kind of applies up here. So now we're going to implicate phi sub c, phi sub e, and phi sub 2e. Okay. So if we write out that equation, it looks like this. So if we include the three cells on the right, our value for phi sub little e is going to be 3/8 phi sub big C plus 3/4 phi sub big E minus 1/8 phi sub 2e. Okay. So we have two different kind of versions of this. Okay. But you can see the coefficients are the same. So in both expressions, we have a 3/8, we have a 3/4, and we have a minus 1/8. So then the question is, you know, how do we choose which one is going to be, or which one are we going to use? Because both of them are valid. They're both kind of 3-cell approximations for the same value. So they both, you know, approximate this phi sub little e right here, and they both work. So then how do we choose which one over the other? So the method at which we're going to choose, or the way we're going to choose, is it's going to depend on the direction of the convection velocity. Because remember, what's unique about convection is that it has kind of a direction that it wants to move the physics in the problem. So when we choose a discretization scheme for the convection term, we always want to kind of put more weight on kind of the upwind side, or kind of the upstream side, or where the you know, where the convection is coming from, because we know that kind of leads to more stable numerics in our simulations. All right, any questions on this? Okay. So what I'm going to do now is I'm going to write out kind of our four integrals again. So east, south, west, and north. And I'm going to give you kind of, each of those are going to have two different cases depending on whether the convection velocity in that direction is either positive or negative. So it's going to be a lot of equations. So, you know, we'll kind of take our time with this. But, you know, the nice thing is that once you have these equations written, translating them into code is kind of, you know, you're kind of just kind of plugging those values in. So let's start. So let's start with the east integral. So we have two different cases here. So our first case is going to be if u is greater than 0. And our second case is going to be when u is less than 0. Okay. So if u is greater than 0, that means our convection velocity is going from left to right. Okay. And then if u is greater than or less than 0, that means it's going from right to left. Okay. So those arrows just kind of indicate that direction. Okay. So the how we're going to evaluate our integral is going to be the following. So we're going to have let's see, u delta times minus 1/8 EW plus 3/4 VC plus 3/8 V sub E. Okay, so this is version 1 of the of the equations that I put on the last page. Okay, and then we can't forget our diffusion term. So our diffusion term is going to be minus k over delta phi sub e minus phi sub c. Okay. And then if our u is less than 0, we're going to use kind of version 2 of what we did last time. Okay. So we have u delta, and then we have 3/8 phi sub c plus 3/4 phi sub e minus 1/8 phi sub 2e. Since the velocity is coming from the right, we're going to involve our kind of 2e neighbor. Okay, so our faraway eastern neighbor. Okay, and then we have our diffusion term. So remember, our diffusion is kind of a process that kind of goes equally in every direction. So we usually don't have to. We can usually use the same thing for diffusion every single time. And then just for completeness, when I say east, what I mean is that we're evaluating the eastern integral. Okay, so that's going to be integral of e of phi v dot n minus k gradient of phi dot n ds. So if you're using the Clique scheme, you know, this integral, it has kind of two different forms depending on the direction of the velocity. Okay, so that's the east integral. So let me write out the same expressions for the south, west, and north. Okay, so this is going to be the south. So again, we have two cases. So we have one if v is greater than 0, and we have another one if v is less than 0. Okay. So v greater than 0 means that the vertical velocity is going up. V less than 0 means the vertical velocity is going down. Okay. And so this is going to be minus v delta minus 1/8 v sub s or 2s, sorry. So this is the neighbor that's kind of two to the south of us. Okay. Okay. Then we have a plus 3/4 phi sub s plus 3/8 phi sub c. Okay. Okay. Then we have a plus k over delta phi sub c minus phi sub s. Okay. Right, so then if v is less than 0, then we're going to implicate the north neighbor. Okay. So if our v is less than 0, we're going to have a minus 1/8 phi north plus 3/4 phi c plus 3/8 phi s plus our diffusion term again. Okay. So these terms are quite confusing, I know, and it kind of takes you kind of have to read it a few times. But notice how in each of these we kind of have a one additional buddy that we never had before. So let's take kind of the south integral just to kind of see what that is. So normally for the south integral, we only have phi sub s and phi sub c, right? But because we're using a higher order scheme, we have the addition of phi sub 2s. Okay, so that's kind of our plus one here, our third wheel. You can kind of think of it. Okay. And then for the other case, we have phi sub c and phi sub s like we usually do. And then our third wheel here is phi sub n. So, you know, it looks kind of normal at first, but remember that we're evaluating the south integral here. So the fact that we have our north neighbor in our south integral is a little bit weird. But because of the Clique scheme, and because we need to have an additional neighbor, which has to be kind of upstream of where our flow is coming from, then we kind of have to include this this third wheel that kind of comes from somewhere far away. Okay. All right, any questions on these? Okay. Okay, so that's 2 integrals down, so we have 2 to go. So let's do the west integral. So once again, we have 2 cases. So we have u greater than 0. So this is left to right. And then we have u less than 0. And this is right to left. So with this, we have minus u delta times minus 1/8 phi 2w plus 3/4 phi w plus 3/8 phi sub c, okay, plus k phi sub c minus phi sub w. Okay. And I just realized I made a mistake on the previous page, but let me finish writing these, and then we'll kind of go back to that. So then if with phi is less than 0, we have minus u delta times minus 1/8 phi sub e plus 3/4 phi sub c plus 3/8 phi sub w plus k phi sub c minus phi sub w. And so the mistake I made last time was I put a k over delta, but there shouldn't be a delta, because I forgot we kind of I multiplied delta kind of all the way. So let me just go and correct that really quick, just for the live notes. So basically, these terms shouldn't be here. So it should just be a k. Okay, so that's the west. So then we have 1 more to go. So let's do the north. Okay, so once again, we have 2 cases. We have v greater than 0, which means the velocity is going up. And then we have v less than 0. That means the velocity is going down. Okay? So we have v times minus 1/8 phi sub s plus 3/4 phi sub c plus 3/8 phi sub n. Okay? Minus k phi sub n minus phi sub c. Okay? And then we have minus 1/8 phi sub 2n plus 3/4 phi sub n plus 3/8 phi sub c minus k phi sub n minus phi sub c. Okay. So yeah, it's a lot of coefficients to keep track of. So luckily when you implement this in code, kind of the code kind of does a lot of that decision making for you. But we'll do kind of one example by hand just so you can kind of see how it is. Okay. So the example I'm going to do is going to be kind of part of the homework that I gave to you guys. So there's one more homework that's posted on mostly on higher order schemes. And so on problem 2, part C, I wanted you guys to apply the Clique scheme to a certain problem. So we'll basically kind of walk. I'll walk you through the first calculation for that. Okay, any questions on these coefficients here?
For the north face, there's no v delta in the beginning?
Oh, there is delta, yeah. Thank you for that. forgot the delta.
Oh,
Yeah,
right.
yeah, they should all have delta.
Thank you.
Okay. So actually, one quick note before we jump into that homework problem. So, you know, just like we saw for the higher order finite difference, in order to actually apply the Clique scheme, you need to have enough neighbors in that direction. Because if you don't have enough neighbors, then you're going to try to get the code is going to try to get a value for a solution that's, you know, outside our grid, you know, which obviously doesn't exist. So unfortunately, this kind of adds another layer of decision making that you have to make for the Clique scheme. So first of all, you have to make a decision based on the direction of the velocity that you which it is. And then after you've decided on which Clique scheme that you want to use, then you have to check, you know, do I have enough neighbors to actually do this? So it's kind of a two-tiered kind of decision tree that you have to do. So for the code, the way that you would implement this is you would have a nested if statement. So you'd have an if statement that first checks, you know, which direction is my velocity going, and then make a decision based on that. And then inside that if statement, you have another if statement to determine, you know, do I have enough neighbors to actually apply my Clique scheme? So it's a bit, you know, complicated, but once you kind of do one, then they all kind of look the same. Before we get into the code, I want to do a hand calculation. So this is homework problem 2, part C. Okay? So I said, let's say we have this problem. Let's say we have minus 32 d phi dx plus 32 d phi dy is equal to 6 d squared phi dx squared plus d squared phi dy squared. Okay. And so before we do anything, let's pick out our parameter values. So from this problem, you can see that our u is going to be minus 32. Okay. Our v is going to be 32, and then our k is going to be 6. Okay. And then since it's going to be relevant to our Clique scheme, let's just write out explicitly the sign of our velocity. So our x velocity u is going to be less than 0 because it's minus 32. And then our v velocity 32 is going to be greater than 0. So that's going to affect which Clique scheme that we do. Okay. And so in this problem, what I want you to do is I gave you two cells. So I gave you cell number 8 and cell number 29. Okay? And I want you to write out basically the algebraic equations for those cells. So for this example, I'll do cell 8 for you guys, and then I'll let you guys handle cell 29. Okay. And so before we do that, there's kind of one more order of business, and that's you know, kind of relating to this top comment here. So if we don't have enough neighbors for Clique, we need to decide what we need to do. So if you kind of watched the lecture from last week, you know that if we didn't have enough neighbors for the higher order finite difference scheme, what we defaulted back to was kind of the basic central difference scheme for that. So for this one, we kind of have two different options that we can do. We can either do a basic central scheme, or we can do a basic upwinding scheme. So either one's fine, but to kind of keep in line with the themes of an upwinding scheme, what I told you in this problem is that if you don't have enough neighbors, then just use a basic upwinding scheme. So let me actually draw you the grid of what that looks like, because for this problem in their higher order, I gave you kind of a special grid. So let's say that we have cell 8 right here. Okay, so below cell 8, we have cell 2. And then to the left of cell 8, we have a cell 7. Okay. So on top of cell 8, we have two neighbors to the north. So that's going to be cell 14 and cell 20. And then to the right of cell 8, we have cells 9 and 10. So we can kind of see right away that on the left and on the left side, or the west side and the south side, we're kind of short on neighbors there, because we only have one neighbor before we run into the boundary of the domain. But on the north and the east side, we have plenty of neighbors that we can use for the Clique scheme. All right. Any questions on the problem setup? Okay. Okay. So now that we know which neighbors are there, and we know which direction our velocities are, so we know our u is less than 0 and our v is greater than 0, let's write out the kind of the algebraic expressions for each of our 4 integrals kind of based on those. Okay, so first we have east. Okay. So if our u is less than 0, that means our velocity going from right to left. So that means we need to implicate our neighbor that's kind of too farther to the east. So this is kind of version 2 of the equations that we did before. And so just a reminder, so then that equation is going to look like this. Okay. So that's the version of our east integral when u is less than 0. So now we have the south integral. So we're now for the south, since our v is greater than 0, we're going to choose kind of the first version of the equation that we did before. So that's minus v delta. Okay. So for the south integral, we have minus 1/8 phi sub 2s plus 3/4 phi sub s plus 3/8 phi sub c, and then our diffusion term. Okay? And so let's look at this south expression here and compare that to what our geometry looks like. Okay? Because we know for the south integral, we're going to need phi sub 2s. We need a south neighbor that's 2 away. So if we go back to our diagram here, and we see cell 8, on the south side, we only have one south neighbor. So then we're not going to be able to apply quick in this case because we only have one neighbor to the south, and that's phi 2. Okay? And so because of that, we can't use this scheme right here. So we're going to cross this out. Okay? And then what we're going to use instead is a basic upwind scheme. Okay? So instead, what we're going to use, since v is greater than 0, then the upstream side of this is going to be our south neighbor. So when we're evaluating phi sub little s, we're going to use just phi sub big S. Okay. So instead, we're going to do minus v delta phi sub big S, which in this case is going to be phi sub 2. Okay. And then we're going to add our diffusion term, which stays the same. Okay. So now we have the west integral. So our west is going to be minus u delta minus 1/8 phi sub e plus 3/4 phi sub c plus 3/8 v sub w, okay, plus k plus k phi sub c minus phi sub w, okay? And so let's check all the neighbors here. So we have phi sub e, so we have that. We have a neighbor on the east. Of course, we have ourself, and then we have phi sub w, so we have one neighbor to the west. So this one should be good to go. So we don't need to make any replacements here. And then finally, we have the north integral. It's going to be v delta minus 1/8 minus 1/8 phi south plus 3/4 phi sub c plus 3/8 phi sub n, and then our diffusion term. Okay. And so for this, we can see that we need a neighbor to the south. We need ourself, and we need a neighbor to the north. So we have all of those guys. Okay. So this one should be good to go. Okay. Okay. So then now that we have kind of these generic expressions, we can go ahead and plug everything in. So we can plug in the indices for our neighbors, and we can plug in our values for u and delta and k. Right? And then what you get after you plug everything in, you get minus 42 d2 plus 6 d7 plus 60 phi 8 minus 34 phi 9 plus 4 phi 10 plus 6 phi 14, all that's equal to 0. Okay. So here's the algebraic expression for cell 8 to evaluate their convection and diffusion terms. Okay. All right, any questions on this? So for the second part of this problem, I want you to kind of do the same thing for cell number 29. Okay? So you can basically follow the same process. You write out, you know kind of the signs of the velocities. Okay. So you know which of the Clique schemes that you want to evaluate, and then for each integral, you need to check just like we did here. So you need to check. See, do we have a neighbor? We have ourselves. We have a neighbor to the east, and do we have a neighbor to e? And if not, then you need to replace that expression with the basic upwinding scheme. Okay? And so cell 29 is on the top right, so it's kind of the opposite of that one. So so the decisions that you make based on the Clique will be a little bit different. Okay, so that's kind of how you do the hand calculations with Clique. So now I kind of want to walk you through the code. Right, so let me kind of share my screen. Okay, so this is the code that I've posted online. So this is a convection diffusion code with finite volumes using a higher order scheme. So this is a Clique scheme method for doing convection diffusion with finite volumes. Okay. So in section 1 of the code, this looks the same as before. So we define all of our values here. Okay. So the length of the domains is going to be 1 and 1, so we're going to have 50 cells in each direction. Okay. Here we're defining all of our matrices and our parameters. And so for this problem, the parameter values are going to be a little bit different. So our diffusion coefficient is going to be 3. Okay, so that's our k value. And then our u and v are also going to be different. So our u is going to be 10, and our v is going to be 75. So these are going to be constant. Okay. So even though these guys are constant, and we can kind of make the decision which Clique scheme to use beforehand, I kind of wrote the code to be general, mostly so that you can kind of use the same template for your final projects, but also just, you know, it's kind of good practice that if you have a situation where your U and V are going to be changing direction throughout the simulation, then your code could kind of effectively handle that without you adding more code to it. Okay. So the next part is section 2. So section 2, remember, this is always where most of the meat is going to be. So the first thing we have is our nested for loop. So we have for I, it goes from 1 to nx, and then for j goes from 1 to ny. And then just like before, so the purpose of these two for loops is to visit every cell in our mesh. Okay. So then after we jump into the for loop, we have these two blocks of code. So the first block is you know, the standard that we always have. So we have to compute our ID numbers for the cell. So first we compute my ID, which is the ID number for phi sub c, and then we compute the ID numbers for the west, the east, the north, and the south neighbors. So all that's pretty standard. So all of these expressions are kind of the same as before. And so just like we saw with the higher order finite difference, you know, we have to add additional code to compute the ID numbers for our neighbors that are far away. Okay? So we have West ID 2, so this will be the ID number for W2. We have East ID 2, so this will be the neighbor for 2E. And then we have North ID 2, so this is the ID number for N2 or 2N. And then South ID 2, this is for 2S right here. Okay. Okay. And so what I'm going to do is I'm going to walk you through the code I have for one integral. So this entire block of code is just responsible for just the east integral, right? So so it becomes pretty lengthy once you're doing higher order schemes. Okay. Because remember, you know, we kind of have to have we have to make kind of multiple decisions here. So we have to make a decision based on the direction of the velocity, and then we have to make a decision based on how many neighbors that we have in that direction, if we can actually compute the Clique scheme. Okay. But before we do all that, you know, one thing that we have to check is that if we're on the boundary, okay, so we have our if statement starts with if I is equal to nx. Okay. And so what this means is that if I is equal to nx, then we're on the total right side of our domain. So if we're on the total right side of the domain, we don't have any neighbors at all on the right or on the east side. Okay? So if we have no neighbors, then what we need to do is we need to apply the boundary condition. Okay? And so that's what we do in here. So to apply, in this case, I have a Dirichlet boundary condition on the right side where phi is equal to 25. So I have the code that implements that. So we have the entry that goes into the left-hand side matrix, and then the entry that goes into the right-hand side vector based on the Dirichlet condition of 25. Okay. And then from here, now we jump into the Clique scheme. Okay. So the next if statement I have is if or else if u is greater than 0. So this tells us that our velocity goes from left to right or west to east. Okay. That means we're going to apply kind of version 1 of our Clique scheme for the east integral. Okay. So if you kind of look back in your notes, you know, we had 2 versions for Clique, and this is going to be our first version. So now that we've determined, or we've made the decision that, or we've checked that our velocity is greater than 0, then we need to check if we have enough neighbors. Okay. So in this case, having enough neighbors means that you know, if I is greater than 1. Okay. So this tells us that you know, we have a neighbor on the west, because version 1 of this, you know, involves our west neighbor. So the only case where we wouldn't have a west neighbor is if I is equal to 1. That means we're totally on the west boundary. Okay. So if I is greater than 1, that means we have at least one west neighbor, so that's good. Okay. So if we have our west neighbor, then we implement those coefficients here. And you notice that there's 3 lines of code here. So the first one is going to be A at my ID, west ID. So this is for phi W. Okay. So this is the coefficient for phi W. So we have minus 1/8 u times dy. Okay. Next we have my ID. So this is same as before. So this is phi sub c. Okay. And then we have A at my ID, east ID. So this is phi east. Okay. These should be capital. So that's if we have enough neighbors. But if we don't have enough neighbors, then we have to rely back onto a basic scheme. So for the in-class example that we just did, we fell back on basic Upwind, but in this case, the basic scheme that I fell back on was just the basic central scheme, where the our phi sub little e is going to be just the average of phi sub c and phi sub e. Okay? So this is going to be phi sub c, and this is going to be phi sub e. Okay. So that takes care of the cases when our velocity goes from left to right. So if our velocity is greater than 0, but if our velocity is less than 0, so that's what this else statement is here. So this else belongs to kind of this family of if statements here. Okay? So what this is saying is that if we're not on the right boundary and if our u is less than 0, then this is basically kind of the last kind of remaining case. Okay. So let's walk through this code. So at this point, since we've entered this else statement here, we know that our velocity goes from east to west, or our velocity is less than 0. Okay. So then we have to have a coefficient for phi sub c. Okay. We need to have a coefficient for phi sub big E. Okay. And then since our velocity goes from right to left, we're going to implicate our neighbor that's 2 away on the east. So this is going to be phi 2e. And then just like we saw up above, if we don't have enough neighbor for Clique, then we're going to fall back on a basic scheme. And this basic scheme is going to be our basic central scheme. So this has coefficients for phi sub c, and then also phi sub e. Okay. So that's the east integral, and then basically all the other integrals kind of follow the same trend. So I'm not going to, go over those, but you follow kind of the same process here, where first you check if there's a boundary condition, then you check the direction of the velocity, then you check if you have enough neighbors. So there's kind of 3 things that you need to check. So it's complicated, and it's a lot, but this kind of combines kind of the best of kind of everything, where you have a convection scheme that's upwind, so you don't have to worry about stability, and you have a scheme that's going to be more accurate than kind of the basic scheme. So this is kind of the best of it. Okay. One thing I will say about this, for those of you guys who are using this for your final project, the Clique scheme isn't quite as accurate as the central difference scheme we did for finite difference. So your result for using the Clique scheme is going to look different than the higher order scheme for finite difference. Okay. So don't be alarmed if they look different. So they should be different. Because Clique scheme is only 3rd order accurate, versus the method that we covered last Wednesday was 4th order accurate. Okay? So there's going to be some differences. So don't be alarmed. But if you want to kind of make sure, if you're not sure what you're getting, then definitely let me know. Then I'm always free to kind of talk about that stuff. Okay. Okay. Any final questions on higher order schemes? Okay. Let me see. Go back to the notes. Okay. So that's it for higher order schemes. So in a nutshell, what you're doing is basically any term that has a convection in your governing equation 0, you're going to replace it with a scheme that's more accurate than basic central difference. Okay. But everything else you're going to keep the same. Okay. So there's no more questions on that. I'm going to start the next topic, which is going to be the last topic we're going to do in this class. Okay. And that's going to be unsteady problems for finite volumes. Okay. And so just like we did in finite difference, kind of the very last thing we did with finite difference was unsteady problems. Okay. And so we're basically going to be finishing up this arc for finite volumes as well. Okay? So remember, the unsteady term, or problems that are unsteady, are basically any terms that have a time derivative. Okay? So if you look at kind of the governing equation for the final project, you can see kind of the first term that we have there is a d phi dt, meaning that we have a convection term, okay? Or a unsteady term. Okay? And so when we implement this with finite volumes, you know, remember kind of the thing with finite volumes that we take our equation and we integrate it over the you know, the domain of a cell. So this one's going to be no different. So, you know, just like we did before, we're going to integrate this. And luckily for us, you know, this integral here it's not going to be nearly as complicated as as convection or diffusion. Okay? Because remember, for convection and diffusion, we had to first apply the divergence theorem to basically get the equation into a better form. But in this case, we don't have to do that, so we can just jump straight to trapezoidal rule. Okay. And so with trapezoidal rule, remember, all we do is we just evaluate our integrand at the centroid of our cell, and then we just multiply it by either the length in 1D or the area in 2D. Okay? So there's no divergence theorem here. So it's, you know, we're not going to integrate this guy and get 4 different integrals like we did before. We're just going to integrate it once and get 1 integral, and then we'll basically be done with it. Okay? So we have basically 2 versions. Okay. So in 1D, our cells are only one-dimensional, so we're going to multiply by the length. So we have d phi dt evaluated at the centroid. Okay, so that's d phi c dt. Okay, and we're going to multiply by 1 delta because the you know, we only have a one-dimensional case. Okay, and then 2D, since we have a square cell, we're going to multiply by delta squared. Okay. And then, so believe it or not, you know, the rest of it is kind of the same. So there's really not too much to unsteady problems. It's kind of just combining everything that we knew before. Okay. Okay. And so to actually, you know, because right now we still have this time derivative, which we don't want. Okay. And so to actually discretize it, we're going to use basically the exact same formula that we did before. Okay, so we have d phi c dt. Okay. So we're just going to use a simple finite difference for this. But instead of doing the discretization in space, remember we have to do the discretization in time. Okay. And so what that means is that we need to add our superscripts, either going to be n or n plus 1. Okay. So this is going to be phi n plus 1 minus phi n divided by delta t. And then both of those are going to be evaluated at phi sub c. Okay? And so what we're going to do is going to plug this in here, and then that's our time derivative term. Okay? Okay? And so the order of business is basically we're going to combine this together with you know, everything else that we've done before. So that's, we're going to combine this together with our convection term, our diffusion term, and our source term. And so, you know, normally, you know, you would have to, or one thing that you can do is you can kind of derive the equations kind of as we always have. But I'm going to show you kind of a kind of shortcut that you can apply, and it applies also to finite difference. Okay, But so basically what we're going to do is we're going to take the equations that we already have for convection, diffusion, in finite volumes, and then we're just going to tack this guy onto the end. And then that's, you know, we're going to get new equations because of it, because we're going to add a term, but, you know, we're going to just kind of build on the stuff that we had before. Okay. And then just like before, you know, because this is time advancement, we kind of have two different flavors of it. So we can either have an explicit or implicit. Okay. And we'll go over kind of both of those guys for finite volumes. Okay. Okay. Any questions on this? My cat is yowling from the bedroom right now. Usually my girlfriend feeds our cat at this time, but she's out right now. So she needs to hang on for 10 more minutes and then I'll feed her.
Can it do tricks?
It can throw up at 4 o'clock in the morning. It threw up at 4 o'clock in the morning last night. We had to clean it up. She's an old cat. She's like 15 years old. Okay, so let's get into explicit time integration. Okay. Okay. And so remember, the key with explicit methods is you know, in terms of deriving the equations, we take basically all of our other terms or all of our convection and diffusion terms, and we evaluate them at time instance n. Okay. And so basically, once we plug kind of everything in, and we have all those phi terms, so phi sub c, e, n, you know, all of our neighbors. And so to get an explicit method, you basically evaluate all those terms at n, okay, and then you rearrange the equations such that you have everything with n plus 1 on the left and then n on the right. Okay. So then this gives us, you know, n plus 1 terms is equal to n. And then once you evaluate everything at n, you know, the same kind of rules apply, where we get a system where no matrix inversions is going to be required. Okay? So it's only going to require matrix multiplication and addition. Okay. And so because it doesn't require the solution of a linear system of equations, explicit methods have the potential to be cheaper, okay? At least on a per time step basis. So each time step is going to be cheaper in explicit and implicit. Okay. The downsides to this is that explicit methods tend to be unstable, or they can be unstable. Okay. Well, remember, stability is determined by your time step size. So if your time step size isn't small enough for an explicit method, then your solution is going to be unstable. Okay. Okay. So let's kind of work it out kind of just as a 1D example. Okay. So I think probably we'll start this and then we'll pick it up next time. Okay. So let's say that we have an equation that looks like this. So you have d phi dt is equal to 3 delta squared phi dx squared. Okay. So we have just a simple unsteady diffusion in 1D. So our boundary conditions are given by this. So we have phi at x is equal to 0. So we have a Dirichlet condition on the left side. This would be cosine of pi t. Next, we have d phi dx at x is equal to 1. And this is going to be equal to cosine of pi t over 2. Okay. And then since we're doing an unsteady problem, we need an initial condition. Okay. So our initial condition, we're just going to use our convenient one. So we're just going to assume everything is going to be 0. So we have phi at x, t is equal to 0, is equal to 0. Okay. Right. And so basically, what we want to do is we're going to use the explicit Euler method and determine the algebraic equations needed to advance this forward. Okay. And then I'll write this again on the next page, but the discretization we're going to use is we're going to use 5 cells, and we're going to use a time step size of 0.001. Okay. All right. Any questions on the problem setup? Okay. So let's see. So we have 5 cells. 5 cells where our domain length is 1. So that's going to tell us that delta is going to be 0.2. Okay. And then given in the problem is that delta t is going to be 0.001. Okay. Okay. And so let's jump into the equations. Okay. So we have d phi dt is equal to 3 d squared phi dx squared. Okay. So there's our equation for this. And so just like we normally do with finite volumes, the way we're going to get these equations is we're going to integrate this guy. So let's integrate. Okay. Notice our integration is in dx. Okay. So that's going to be important because our first term here is a derivative in time. So if we take the integral of this dx, then that doesn't change anything. Okay. So what we can do is we can just directly evaluate this with trapezoidal rule. Okay. And then what we get is d phi c dt times delta. Okay. Right. And then on the right-hand side here, we have the integral of our diffusion term. So here's kind of the shortcut that I was talking about earlier. So instead of actually, working through this integral and working through everything, we already know what, the discretization for the diffusion term is. Okay. So for this, we can just plug in FVM discretization for diffusion. Okay. And so that looks like this. So we have 3 divided by delta times phi E minus 2 phi C plus phi W. Okay. Okay. And so what we can do from here is that we can replace this with our time derivative term, or a discretization of time derivative. Okay. And so this is going to be phi sub c at n plus 1 minus phi sub c at n all divided by delta t times delta, okay, equal to 3 over delta. Okay. And since we're doing an explicit method, what we're going to do is we're going to evaluate all of these guys right here, all the guys on the right-hand side, which is basically all the phi terms that come from diffusion, and we're going to evaluate that at n. Okay. So this can be phi E at n minus 2 phi C at n plus phi W at n. Okay. And so we've done all the plugging in now. So now what we need to do is we need to rearrange such that we have all the n plus 1 terms on the left, and we have all the n terms on the right. Okay. Any questions on this? I think probably we'll pick it up next time. Okay. So that's all we got time for today. So we'll pick it up here on Wednesday. So we'll finish this example and just to see how it is. And then after that, we'll continue on with these lecture notes on unsteady finite volumes. Okay. Okay. So I'm gonna double check the coefficients on the starter code for finite difference just to make sure that they're okay. And then I'll give you guys an answer. If not by tonight, then probably early tomorrow morning. Okay? So hope everyone has a nice evening. Please stay safe and please stay healthy. And I'll see you guys on Wednesday. Thanks, everybody.
Professor, could I see the previous page?
Yep.
Thank you.
Professor, I got a question on the project.
Sure. What's up?
So when doing the higher order scheme, do we turn off the regular coefficient codes that we had, and then we run? Okay.
Yes, but only turn off the convection ones. So there's kind of two parts. So there's the regular, or kind of a block for regular diffusion coefficients, and then a block for regular convection. So when you're doing the higher order, only turn off the code for regular convection. So okay. You can turn that off by commenting, and then keep the diffusion there, and then keep the higher order stuff. So yeah.
Okay.
Okay. Any more questions? So remember, the project's due on May 18th, so that's going to be the Monday after finals week. Okay, so I'll probably make a rubric tomorrow, and then I'll post that online, just so it'll be kind of official. So just to give you guys a week. Okay. All right, so I'll see you guys on Wednesday.